It's so good to have you here. Great seeing you. Wow. Man, what a day. What a day, what a day, what a day. All right, so I have been diving into neural networks, and it's been fun. And what I don't know, and I mentioned this in my last video, maybe even the first video, is it seems to be really good at things that random forest already does. So why would you use neural networks if you can use random forests? And I mentioned some of the reasons. I don't remember what they were. They perform better when you have lots and lots of data, apparently. So random forests can get pretty bogged down with lots and lots of data, but neural networks tend to do better, apparently. But more importantly, when you have really complex structure that is hard to mathematically model with decision trees, neural networks tend to do a pretty good job. And it's also really good with unstructured data. Like, as a statistician, I really like tabular data, meaning you have each row representing an individual, each column representing a variable. But if you have something unstructured, like images or audio or text, neural networks do really well. And they also shine when you really don't care about interpretation. You just want to predict something. So I've done a lot of work in the last week. So flexplot has a bunch of tools, particularly compare.fits and estimates, that are supposed to work for any model. And they don't natively work for neural networks. So I created a new R package called flexNN, or flex_NN, for flexplot neural networks, which you can download on GitHub using the link in the description. And you're welcome to use it. It's probably super buggy right now because I just started developing it like 2 days ago. And anytime I release a new package, there's a lot of bugs at the beginning. And we'll probably find a bug today. But the purpose of this video is I'm just going to do what I would do with random forests, and then do the same thing with neural networks and see how they compare. So let's jump right into R. So here I am. I'm going to require flexplot because then I can use all the functions in flexplot, which are embedded within flexNN. I'm going to require tidyverse because I always require that, and party because I'm going to do some random forest stuff. And then I'm going to require flexNN, or that's what I would do, but I am within an R package, and so I'm going to hit Command-Shift-L, because that's what you do when you are in an R package. If you don't know what I'm talking about, don't worry about it. All right, so this is a study on, I don't remember all the details. I found it online. It's got free data. Love it when they do free data. And basically, they're inviting people into a lab, giving them a scenario about some terrorist organization and whether they would choose to bomb that terrorist organization. And in some of those scenarios, there was a civilian who would get killed if they chose to bomb that target. And sometimes that civilian was a known enemy to the state, and sometimes it was like an innocent farmer or something like that. So the details of the study don't matter that much because I'm not going to spend much time interpreting the actual study. What I'm going to be doing is I'm going to be comparing the two models and see what they pick out. And I'm choosing this data set, by the way, because I think I mentioned this in one of my most recent videos, that I was analyzing these data in a live class and things just weren't working out with random forests. And it was kind of lame because I told the class, hey, random forests are amazing. And then I started analyzing the data and they didn't do too amazing. And so I wondered if the neural networks would do better. So I'm going to read in the data. And then I just did a lot of renaming the variables. It's got these weird code names. And then I just gave them new names because I like names to be interpretable. And eventually, if we decide to interpret this, which I don't think we will, I'll give you what the actual questions were about. All right. So I'm going to start by doing a random forest. Actually, I should put that set.seed up here because random forest relies on random numbers too. And so I'm trying to predict fire, whether the participant would choose to fire based on all the variables. And let's see what we get. Okay, now we get metrics that make sense. So out of bag accuracy and prediction. So 86% of the time it makes the correct guess on whether that person will fire or not. That's pretty good. And that's out of bag. Or in other words, that's on the validation set, not the training set. And then these are variable importance metrics. And so the top predictor is civilians deserve to die. So if the person believes that, what does civilians deserve? Let me read the actual question. PS Des. How much does a second person who is already in the farmhouse deserve to die? Yeah, so I guess they're targeting a farmhouse where there's a known ISIS operative and there is a civilian in there. And the biggest predictor of whether they will fire is whether that civilian deserves to die. Make sense? Guilty, I think, again, that's referring to the innocent person, whether they are guilty of some offense or not. Anyway, enemy deserve to die, and teleology. Teleology is the greatest good for the greatest number of people. That's one of the questions. And we got a bunch of other predictors. So those are the top predictors, and that is the accuracy. Now let's see how the neural network does. And so I have created a function. You guys are going to love me, maybe. Although if you're using neural networks, you're probably using Python, so you might not care either way. So I created a new function called NN that it's an easier interface, I think, for using neural networks because it can take a formula and a data set. So it follows the same convention that flexplot follows, and it has a bunch of additional arguments. If you wanted to learn more about it, you can go $NN, and it'll tell you what arguments it expects. And so we will review this. So layers. So that's one of the problems is like how neural networks are normally set up is you got various steps. Actually, I'm going to go ahead and bring that up. NN. Well, you got to define the type of model, then you got to add the layers, and these layers came from here. And then you've got to compile it with your loss function, what optimizer you're using, what metrics you want to keep, and then you've got to fit it with history. And all that I find difficult to remember and kind of tedious. And I would just like it if it just had default features, and then the things that you want to specify, you just specify. So anyway, restructured it so it looks like that. So we got layer dropout, which is a new argument that I didn't tell you about. So basically what it does is after one layer, it randomly sets 30% of those layers to 0. So those neurons basically go away. And the purpose of that is to prevent overfitting. And so our first layer has 16 neurons, and the activation is RELU, which again is that one that says anything below 0, get rid of it. And then dropout rate. So 30% of those were set to 0. And then the next layer has 8, and its dropout rate is 30%. And then at the end, we're going to have a sigmoid function because it's a binary outcome we're trying to predict. And I heavily relied on ChatGPT to set those defaults. I'm new, if you don't remember. I don't know enough, I don't have enough experience to make intelligent guesses about how to modify these. So I just asked ChatGPT. If you do know, and of course, if you see something wrong with this, then please let us all know. All right, so once we set the layers, then we specify the formula. So we're saying predict fire from everything else. We are using the data set that we brought in earlier called D, and then we are using these layers. And then the loss function is binary cross entropy. Not exactly sure what that means, but again, it's one of the suggested ones for a binary outcome. And then I am asking it to track accuracy as well as area under the curve. So if I do all that, oops, got to read the layers in first. So it runs, and then I've also created a function called estimates that computes relevant estimates for the neural network. So if I go NN_estimates, we get variable importance metrics like we do with random forest. And they both agree that civilian deserve to die is the most important predictor, and guilty was that next. Let's just compare them side by side. So I'll go NN estimates $importance. And then if I go RF mod estimates $importance. And if we look at the neural network estimates and then the random forest estimates, both of them agree civilians deserve to die is the most important predictor, followed by guilty. Now the neural network is saying hospital never target. Let me see what the actual question is. The actual question they were asked is, in war, military should never target non-combatant personnel or buildings for military strikes, even if it is strategically advantageous. I put hospital for a good reason that I'm not going to go into right now because it doesn't matter. All right, so they're not in exact agreement, but they're close. So the rank order is not exactly the same, but they're really, really close. So that's good. I'll make a note. They look to be pretty close. All right, now, and this is the thing that was the biggest pain, is let's visualize things. So I'm going to do compare.fits. And this took a lot of time to get that to work with neural networks. So I'm going to go fire, tilde, and I'll just go ahead and put civilian deserve, and I'll just leave it at that. I like looking at the bivariate effects first before I start looking at more complex relationships. And then I'll go data equals D, and then rf underscore mod, and then nn underscore model, $ model. In the future, you will only have to put nn model because that's kind of inconsistent to me. It's not there yet, and it wouldn't be hard to put it there. I just forgot. So let's go ahead and see what this looks like. Okay, so this is what we get. And one thing I'm going to do is I'm going to do a logistic overlay. And if you saw one of my more recent series about plotting logistic regression, you'll know what this is doing. It's basically converting a binary outcome into a scatter plot. And then I will go alpha equals 0.1. And I'll tell you what that means in just a minute. So the alpha 0.1 made the actual dots kind of disappear. And then the logistic overlay is binning the values and telling you what proportion scored between, it looks like, 1 and a 2, and then between a 2 and a 3, and 3 and a 4. And so at this level, it doesn't look like they're doing a very good job at all. Neither model. Now, in some ways, it's kind of not a fair comparison because we're looking at this bivariately. And the models are conditioning on everything else or assuming everything else is constant, which you can't make that assumption. And so we don't expect it to fit perfectly. But usually they do look okay, but that doesn't look very good in this case. So that's okay, maybe. Let's go ahead and look at, let's see, what are, so we're going to look at, I'm just making a note of what I need to look at. Look at civilian, deserve, guilty, enemy deserve, teleology, and then let's see, am I missing anything else? I'll go hospital never target. So I'm taking the first 4 for both of them. All right, so we did civilians deserve. Now let's do guilty. That's going to be a problem, though. We're going to have to do a magnet plot. So magnet plot. And again, if you saw my recent series, you'll know what this is about. So I'll go fire, tilde, guilty, data equals D. And so both models say that guilty is an important predictor. And those blue dots represent the prediction from a logistic model, but they don't represent the prediction from these models. So, I mean, that's good because we see like there's a huge difference between the two predictions. So I guess it's not surprising that both of them suggested that. Let's go ahead and try teleology. And again, comparing both models. And I hope you work. Okay, once again, we get a situation where the models aren't doing very good at the bivariate level. And to me, that seems to suggest, okay, let's think about this. So those scatter plot dots are basically looking at what we actually observed. So it's taking those with a teleology score of 1, I think it is, and computing the proportion of individuals who chose to fire versus not if their teleology score was 1. And then it's doing that for those who are 2, and then 3, and then 4, and then 5, 6, and 7. Yeah, because teleology is a Likert scale. So those are the observed. And the model is predicting very different from that. Why is that predicting very different from that? Well, what it's doing is it is holding everything else constant. So it is assuming that all the other variables are at their mean. But that may not be the case. Whereas what the model is doing is it is assuming that teleology changes while everything else is held constant. Or in other words, it's assuming you can get significant changes in teleology and nothing else changes, which is an unrealistic assumption, because that would suggest that essentially teleology is not correlated with any of the other predictors, which it probably is. So it doesn't surprise me. No, it still surprises me, but it does, it's easy to understand why that might happen. I'm going to guess that that's what's happening, that teleology is highly correlated with some of these other variables, as it should be, because there's so many questions that essentially ask the same thing. So the teleology question is asking, during war, it is acceptable to carry out a crucial military strike if some civilians would die as an unavoidable side effect, as long as more lives will be saved in the long run. And then another question is very, very similar. It says, during war, it is acceptable to carry out a crucial military strike if some civilians would die as an unavoidable side effect. Those two questions are basically asking the same thing. So it seems unreasonable to suggest that as you increase the responses on one, that the others will remain unchanged. They're going to be highly correlated. So I'm guessing that's what we're seeing. This is the reason why this fits poorly is because of multicollinearity. Perhaps. Now let's go ahead and look at the next variable. And again, we're seeing that same pattern. And that actually makes perfect sense when you think about it. That if only this variable were allowed to change and none of the other variables were allowed to change, of course you would see a weak relationship. But what you actually observe is a very strong relationship because some of the other variables are going to be changing along with it. So yeah, the model would underestimate it if it held everything else constant. Makes sense. Let me think about that. So this may be a terrible approach. And this argues why neural networks might be better than random forests. So we've got a bunch of variables that are very, very related and essentially asking the same question. And what we are trying to do with the neural network and with the random forest model is we're trying to isolate the effect of a single variable. So if we're asking about the teleology variable, we want to know its unique contribution above and beyond any of the other variables. But some of those variables are extremely correlated, and so its unique contribution is going to be tiny. So this is a case where random forest probably doesn't make sense to use at all, nor does it make sense to use neural networks as I'm trying to use them, where I'm trying to estimate the value of specific variables. Okay, let me pause the video and think about this for just a minute. I'll get back to you. I'm back after some research. Okay, so let me just summarize the problem. Historically, when I have tried to visualize the predictions of a model, I've done so by creating a data set where every predictor value is set to its mean, but the 1 or 2 or 3 variables that I want to vary. And then let's just say it's one variable. Let's say it's the teleology variable. In that data set, I replace the mean of teleology with 1, 2, 3, 4, 5, 6, and 7. Or in other words, I have a data set where the only thing varying is teleology. And then I feed that into the model and ask it what its predictions are. Great strategy, except the problem is I am creating a situation that is completely unrealistic. Especially with this data set, where teleology is highly correlated with another variable. And so it's very unreasonable to assume that no other variable is going to change as teleology is changing. And so you end up getting predictions that look like what I saw that just don't seem to fit the data. And they don't, because that's not how the data are behaving. And it's not because the model is wrong. It's because the way that I'm evaluating the model is wrong. So what do we do? Well, there's 2 problems that we have to address. One is computing variable importance. The way that I'm currently doing it with both random forests and neural networks is that I am shuffling the scores. So I'm comparing the fit with the existing scores and then shuffling. Let's say we're talking about teleology again. Then I create a new data set that is exactly like the original data set, except the teleology scores are shuffled. And then I make predictions based on the shuffled scores. And variable importance is just computing the difference in prediction or in accuracy between the two models. And the basic idea is if you shuffle the scores, you break any statistical relationship that variable had with the outcome, essentially making it noise. And if you compute the difference between what you actually obtained and noise, you should see a large difference. That's how the variable importances are computed in this case. But again, that's problematic because you're interpreting these variables in isolation. It's similar to what I'm doing here, where you're saying, what happens when I just shuffle these scores and no other scores? Well, that's not a very realistic assumption. People have thought about this estimating thing before, and there are things called SHAP and ALE, which stand for... So ALE is accumulated local effects, and SHAP is Shapley additive explanations. And both of these are basically saying, all right, let's allow these variables to correlate, or given how variable A interacts with and overlaps with variable B or whatever, and others in the actual data, how much did A contribute to this prediction? That's what Shapley is trying to answer. And ALE asks a similar question. It says, how does variable A influence the prediction averaged over real data points where variable A changes and other variables are what they normally are? Fortunately, there's already metrics out there that we can use. Visualization is going to be a little more tricky, I think. So I have two ideas, and I'm not sure which I'm going to use. Probably try both of them. One, and I keep looking off screen because I'm trying to remember the interpretation of these things. So how do we visualize this? And let me just read again what ALE is telling you. It says, how does variable A influence the prediction averaged over real data points where variable A changes and other variables are what they normally are? To me, it seems like you could do that in R. So instead of generating a data set that has the mean for everything and then artificially varying one of those variables, instead we could take real values from the data set. And if we're trying to average teleology, we can use the data set to compute the averages of the other variables within the values of teleology or whatever. That seems like a fairly easy fix. And maybe that'll be more informative. And so if I do that, I have a visual that represents what the model is likely to predict given how these variables are correlated, which is helpful. And it's going to give me estimates that reflect how the data actually behave, which is also helpful. But I think one thing that I need to eventually address with this data set is that there's some clustering going on, that these variables are highly correlated to one another. And if I ignore that fact, that's a problem. And, you know, earlier I said one of my goals is to figure out where neural networks are going to be useful, and I think I've just figured out where they're going to be useful. Because I know that within a layer, neural networks are essentially creating latent variables or representations, which I've talked about. And I would like to know what those representations are. Whereas random forest doesn't do that. It doesn't create representations. So I think that's what I'm going to try to tackle next. I'm going to try to adjust the estimates for both random forest and for neural networks to give me both the permuted variable importance, but also the ALE, accumulated local effects, or the SHARP value or SHAP values. I want to modify them both so they can do that. And I think I'm also going to modify how the visuals display things. Or instead of fabricating these artificial data sets that are unrealistic, we use the actual data sets. And I also really want to look at this clustering thing. Because to me, that seems like the most promising area for neural networks, is its ability to identify these representations. And I actually don't know at this point if this is going to be a separate video. It probably is, because this feels like a daunting task. It feels like a lot that I have to do that's not going to just take me 10 minutes to do. So unfortunately, I didn't get very far today. But no, I did get far. Like, I realized the limitations of neural networks and random forests and the approach that I've been using for years. I feel like I should be way more depressed about that. That this approach that I've relied on for years fails miserably in situations like this, where you have super highly correlated predictor variables. But I'm actually not all that depressed about that because I always love opportunities to refine my approach. Anyway, I think I am going to end it there for this week. And I hope you will join me next week where I actually make these tools and see what kind of value they provide. And if you didn't know, starting in less than a month, I am doing a mixed models class that starts in September. So if you want to take a live class in September about mixed models, please join me. And if the live classes don't work for you, you can take the self-guided classes. I've got an R class, I've got an Introduction to Simplistics class, I've got a machine learning / visualization class. Doesn't have neural networks in there right now, but I may add that later. And I've got a mixed models class. So I hope to see you soon. Hey, it was great hanging out with you. Peace out. I don't know. I just want to get upset. Let's read some comments and questions, shall we? Power calculations for mixed models suck. I invented Blue Pill so that one can escape from the simulation of the Matrix. Whatever, I don't care. I don't want to do this anymore. I don't want to worm. It doesn't have it at the end? No. No, it's got to have it at the end.